Hey boy, what you doing? Hey boy, where you going? Who's that boy? Who's that boy? It's Evan. All right, welcome back. Let's get started again. I hope your test was okay. And if you're watching this before you take your test, I hope it goes okay for you. I'll try to get them graded by the end of this week. I was able to, I think a lot of you are backloading the exam, which is the same thing I would do too. I would take it as late as I could so I could study more. But because of that, my guess is that today on Monday, I'm going to be getting approximately half of your tests back, like turned in. And so that means I won't be able to start grading the tests for half of you. Basically what I'm saying is if you turn it in on Monday or even late Sunday night, it's more likely that I won't be getting them back to you as early as I got the early ones, because of course I can grade all the ones as they come in, but I eventually get out of sync with the ones grading, especially when I have to record these videos. But I would say you can probably expect them by a week from today, so a week from Monday. You can expect to get your score. The nice thing is that you'll get your score right when I grade it. So just go ahead and look forward to that. Without further ado, we'll get into today's topic, which is the area between two curves. And I don't think it's a terribly difficult topic today. I think it's actually a pretty nice one. It'll turn out that I'm just going to give you I'll give you the formula right now, and then we'll figure out why that's the formula and why it works and how to use it. So let's just look at the formula for the area between two curves. So given f of x and g of x, the area between f of x and g of x from a to b is given by integral a to b of the absolute value of f of x minus g of x dx. And this is the way that like we naturally want to think about it, is it's just the absolute value. But when you're actually computing these, it's a bit easier to talk about it as the top curve minus the bottom curve. That'll save you some hassle in actually figuring out how you're going to calculate the absolute value. So it's one thing to write down the absolute value sign. It's another one to actually calculate what that is. What it actually means is it's the top curve minus the bottom curve, because an absolute value basically says no matter what, if something is negative, make it positive. If it's already positive, leave it the same. And you're going to solve that problem by taking the top curve minus the bottom curve, because if you have the top curve, it's naturally going to be bigger than the bottom curve. So if you subtract off something smaller, it stays positive. And that's how you can, guarantee that the absolute value sign is always there. So let's answer the question as to why now. Why this is the area. And I call it the total area. Just think about it as the area. Total area between the two curves. Well, let's think about this in terms of the regular definite integral. So in terms of the regular definite integral, something like this was the area between f of x and the x-axis. And we saw that was true. This is true so long as f of x is positive. Or 0. So we saw that that definite integral was the area between f of x and the x-axis. So that was basically this area. I'll draw it here now. That's f of x. There's a, there's b. That was this area, right? I think you guys can all agree with me that that's what was going on there. In terms of regular definite integral, this thing gave the area. So this A is the area here, A. And second, if we have g of x, let's call it strictly less than f of x, and let's make it greater than 0 still, then this integral, call this capital B now, is the area, there I say but the area between f of x and the x-axis. This is the area between g of x and the x-axis. For example, let's make g of x something like this. Still call that A, still call that B, and here's g of x. So this would be capital B. So if we look at the two of them now, if I take this integral of f minus g dx from A to B, well, my integral sign lets me do this, right? It lets me take f of x dx, I can split it up at that minus sign. And what is that? That's the area A minus the area B. And what does that look like pictorially? What did f look like? That's pretty simple. F was like this, and then G was something like that. And I can look at this whole thing was A. So this whole piece is A. And then B was this piece down here. And so this is just like I've taken some scissors and I have area A and area B, and all of a sudden if I take area A and take some scissors and subtract, I literally am cutting out the area of B, I end up with the area of A minus B, and that's exactly equivalent to the integral of f of x minus g of x. Now you'll notice that was special because f of x was always greater than g of x. I'll say this is a special case. Since f of x is always greater than g of x. But if they had switched places, rewrite that. If they had switched places, it would have been g of x minus f of x. So whatever it is, it's always the top curve minus the bottom curve. Hence, integral a to b absolute value f of x minus g of x, finish the absolute value dx. So there's your pictorial representation as to why this is talking about the area between curves. But of course things get a little bit more complicated than this. So let's talk about the complicated cases. We'll do let's do, so just I'll just draw it out and then we'll handle an example. So the complicated cases are something like this. So there's f, and then here's g. So f looks something like this. Color that in red so we can keep track of it. And g looks something like this. Keep track of that one. So the area between them, color in blue, is of course all of this stuff. And let's suppose that we chose A and B correctly, so that it's just happening at these intersection points. Put A right there, B right there. And then I'm going to call this the point C. So notice everything switches. At x equals C. So the way we would handle this is by breaking up the integral. And this makes sense. If it's like the absolute value function, it's like a piecewise function, and piecewise functions get switched. They get broken up certain places. So really the integral of f of x minus g of x in absolute value dx, a to b, this is equal to the integral from a to c of the top minus the bottom. And what is the top between a and c? Top between a and c, well actually we'll just write this out then, top bottom dx plus the integral c to b top minus bottom dx. What is that? The top function on the left hand side, it's the red function, and the red function is f of x. Make sure we know that here. So it's red over here is the top one, and red is the bottom one there. So this is f of x, and then it's the green function on the other parts, right? The green function is the bottom over here, g of x, and the top function over here, g of x. So basically, we just want to be careful if they ever change places. Integral a to c, f of x minus g of x dx plus the integral c to b g of x minus f of x dx. So that's kind of the way you would handle the complicated cases where things switch around. And so then let's talk about a subset of the complicated case. This is the integral of the absolute value of f of x dx. This would give the total area between f of x and the x-axis, also known as the function y equals 0. And why is that? Well, that's since this is really just the integral a to b f absolute value f of x minus 0 dx. So these are your two functions. In some sense, these are your two curves now. So what I said earlier was that the definite integral from a to b of f of x equals a, right? But I said here, so long as f of x is positive. That's important because if I took the absolute value of something positive, it stays positive. So there's really an absolute value going on here too. And the same thing here, I made g positive, so that's what I needed here. It's really the absolute value of g, and so on. So now this new formula, absolute value of x, does not require that f of x is positive. Area between two curves. So my two curves are really just f of x and 0 there. So let's do an example of this second one, and then we'll do an example, the arbitrary example instead. So example, total area of x cubed from -1 to 3. So the total area of x cubed, right, that's a special thing here. Since x cubed can be negative, I'll draw it out really quick. X cubed looks like this. From -1 to 3 is here, and then up there. So that's the area we're looking at. But regularly, a normal integral would call this piece on the left negative when it's not. So we call that area negative. And sometimes we want that. Sometimes it's actually helpful to talk about that as negative area. But today's just not that day. We want the total area. And so that's why we take the absolute value from -1 to 3. And what happens is we just ask ourselves, where do the curves intersect? And remember what our second curve is. Our second curve is the x-axis. So where does the function hit the x-axis? Where does the function hit the x-axis? And the answer is at x equals 0. So we split the integral there. And we split the integral at 0, it gives us integral -1 to 0 x cubed dx plus integral 0 to 3 x cubed, these are still an absolute value, dx. But what's special here is that everything here, x cubed is always negative here. And x cubed is always positive here. And so the way that the absolute value would work is that it would make this half, two negatives make a positive. So the absolute value would add a negative sign in, and it would do nothing to the positive half. And so then we can just compute these as they would be, negative x to the 4th over 4 from -1 to 0 plus x to the 4th over 4 from 0 to 3. And what would we get? We would get -0 minus 1/4 plus 3 to the 4th over 4 minus 0. And so now we see why the two negatives, these two negatives right there cancel each other out, and it keeps everything positive. So this is really 3 to the 4th, which is 81 plus 1 over 4, so really 82 fourths, and that's like 20.5, or 20 and 1/2. So that's how you would do it for just a regular function, and basically this is the x-axis now that we're using. Or now we'll do an example with two actual curves. Find the total area between f of x equals x minus 2 squared and g of x equals x minus 2 squared plus 1, or sorry, negative x minus 2 squared plus 1. And you'll notice I didn't put x bounds here. Sometimes you have to solve them for yourself. Sometimes you have to figure out the x bounds for yourself. We'll see. I'm going to graph these, and then we'll see if you guys can come up with the x bounds for me. Let's graph the functions. So f of x looks like this. This is the point x equals 2. It's a parabola. And g of x looks like this. It's a downward facing parabola. I guess it intersects 1 right there. That's good enough. So this would be g of x on top, and then this is f of x on bottom. And I'm just going to outline them like I always do so we can keep that in mind. You'll notice that they intersect each other here, but they don't switch signs anywhere. So that's kind of nice. It's going to make our life a little bit easy. So it's the g of x line and the f of x line here. And then now we want to put our thinking caps on and figure out what it means when it says find the total area between. And hopefully everybody looking at this graph can agree with me that this is the total area between. So if that's the total area between, we just figure out where they intersect each other. So we ask, where are the intersection points? And we can find these algebraically by setting the functions equal to each other. So you set the functions equal to one another and solve for x. So in this case, our functions are x minus 2 squared, and we set it equal to negative x minus 2 squared plus 1. And as always with these, you always want to bring everything with an x to one side and everything without an x to another side. In this case, it'll turn out to be a quadratic, so we're going to do something slightly different. But the first step is the same, right? So there's this one term, this x minus 2 squared on both sides. I'm just going to bring them to the same side. And since there are two of them, I end up with 2 equals 1. And so, okay, what is this equivalent to? This is x minus 2 squared equals 1/2. Rather, x minus 2 equals plus or minus the square root of 1/2. Or what does that say x is? It says x is 2 plus or minus the square root of 1/2. And like, yeah, okay, square root of 1/2 is maybe not the prettiest number, but we'll just keep that in mind. This is not impossible to work with. So these are our bounds. So if I scroll back up here, that's telling me that these points here, this is 2 minus the square root of 1/2, and this point is 2 plus the square root of 1/2. And so then what is the total area? Well, total area, I'll denote that TA. Say TA is the integral from 2 minus the square root of 1/2 to 2 plus the square root of 1/2 of the top curve minus the bottom curve dx. And hopefully somebody can scroll up, tell me what the top curve is, at least in that interval. In the interval, the top curve is g of x. And in that interval, the bottom curve is, of course, the only other choice. And if we remember what they were, g of x was negative x minus 2 squared plus 1, minus f of x was x minus 2 squared dx. And then, I can't stress this enough, you always want to simplify your expressions before you try to take an integral. So let's try to simplify this. This is really a negative. It's really negative 2. If you simplify this, this is negative 2 integral x minus 2 squared dx. The bounds are the same. Plus the integral of 1 dx. And the integral of 1 dx is easy. That's just x. And this other integral, it might look a little tricky right now, but we should be getting pretty good at u substitution. You use your priorities with u substitution, you're going to get to the fact that this has to be what's in the parentheses. What's in the parentheses is x minus 2, so u equals x minus 2. Makes a du equal to dx. And so this would become negative x minus 2 cubed over 3. If we use u substitution, that's definitely going to be what it ends up being. So go ahead and work that through if you don't quite know how. And this is just x. And then we just plug them in, and we're happy. So plug the top number in. Turns out that this is 1/2 to the 3/2 over 3 minus, now this is going to be negative 1/2 to the 3/2. Right. Divided by 3. And then this will just be, I guess this is going to be 2 plus root 1/2 minus 2 minus root 1/2 So the 2's over here are going to cancel. We have 2 subtractions of the 1/2, so we really end up with 2 root 1/2 minus that and this negative sign. I'm just simplifying even though I don't require it on exams. That negative sign and that negative sign are actually going to, doesn't look like it, but they're going to go together. Sorry, I did that. To give a positive, and so I end up with 4 times 1/2 to the 3/2 over 3. So that's, that's a crappy number, but that's what you get sometimes. But that's how you would handle a different problem, maybe where it's not telling you. My cat's meowing. She wants out of the room. Okay, I'll let you out of the room, Jill. And then, so that's how you would maybe find the bounds if it doesn't give it to you. And then there's one extra thing that the homework maybe is going to have you, a special way that it talks about the problems that I just want to cover. So this is the way your homework introduces some problems. It'll say something like, find the area bound by f of x, g of x, and the lines, the vertical lines, x equals a and x equals b. And you're just supposed to interpret these vertical lines, interpret this part about vertical lines as over the interval a to b. So it's the same as we've always been doing. It's the integral from the bottom x value to the top x value, but it just likes to talk about the vertical lines. And that's because sometimes we could have, maybe we have functions like this, f of x and g of x. And maybe it puts, so maybe this is a and maybe this is b. And then our total area would be actually something like this. So you would still have to calculate this intersection point. So you would still have to calculate this. So you'd still find that point and then split the integral up into this piece. Say call it C. And then your area would still be, so it's still the integral. This formula will never get you wrong. It'll never do you wrong, but it just doesn't make as much sense as maybe saying, in this case, this would be a to c of g of x minus f of x dx plus the integral c to b f of x minus g of x dx. So that's the way that your homework might introduce these problems. Oops, didn't want to do that. I want to do this one in red. That's the way your homework is going to introduce some of these problems. So just think about those vertical lines as your x bounds. That's what you want to think about them as. And otherwise, it should be relatively straightforward. It asks you to sketch the graph, but I know that you guys are just going to keep trying the problem multiple choice wise until you get that right. So don't worry about those as much. Anyway, that's all I have. I'll see you all tomorrow. Bye.